already have, and so that is what 8.4 is. And so we're going to be looking at what we call our comparison tests. And we have two that we'll be working with, and that would be direct and limit, but they both are just comparing what we call a basic series or basic test that we already are familiar with. So we have our geometric, right? So the geometric is the one that has, some sort of coefficient and then some sort of ratio to the power of n. And then our p series is when we have 1 over n to some sort of power, right? And then our nth term test is when we take that limit to infinity of whatever that sequence is, and as long as it doesn't equal 0, then we know it diverges. So it doesn't help us with convergence, but it will help us with divergence. Does it diverge, or like guaranteed divergence? Okay, so these are, so most of what we're going to be using though is right here, geometric and p-series, and so these are the ones that we need to be familiar with. So what our direct comparison test tells us, so this is what we call a direct comparison test, given two different sequences, whatever those happen to be, if the sum of the sequence converges for Bn, then the sum of An, or the series, would converge as well. So it's important to note that when we talk about An and Bn, that we're talking about one sum is bigger than the other, right? So one set of numbers is bigger than the other. So we're calling B of n our bigger value for this particular moment. Doesn't always have to be that. Just make sure you keep that in mind. And then An will be our big one. So what we're saying here is that if we know that Bn, which is our larger termed series, so if this is our larger termed series here, if it converges, then one that is smaller than it would have to converge as well, right? So if we knew like all of the terms here, so like say 2 plus 1 plus, I don't know, a third plus a ninth, and so on and so forth, if we knew that this added up to a finite value, and then I look at one that has all smaller terms, so maybe it starts at 1, right, and goes 1 plus a third plus a ninth. So this would be a smaller one, right, because I chopped off that 2. It would have to converge as well, right? So if the bigger termed series converges, the smaller termed one has to converge as well, right? So what about the other way? So what if we take a look at, well, if the smaller termed series diverges, then the larger termed would have to diverge as well, okay? And so again, that would just be like the same exact note, right? Like if I took a look at the smaller termed one, so the 1 plus a third plus a ninth, so let's say that this added up to infinity, and then I added, a 2 to the front of it. So now all of a sudden it's a bigger one, right? A bigger termed series. It would have to diverge as well, because if this is going to add up and shoot off to infinity and I add 2 to it, well, it's going to add up and shoot off to infinity as well, okay? So the flip side of that is not true, right? So if you have, say, the smaller termed one, so if we said that, An, so the smaller one converged, then you don't know anything about Bn. Like this would result in no conclusion, because if the smaller one converges, who's to say the bigger one will converge as well? Like maybe it's just enough bigger to add to infinity. So we have to keep that in mind, that when we're talking about this particular test for a direct comparison test, is that this only goes one way, okay? So we need to make sure that we're tracking that information, that if the bigger termed series converges, the smaller one would converge. If the smaller termed, right, because I'm referencing this inequality, diverges, the larger termed one would diverge as well. Okay, so how do we go about doing the direct comparison test? So to determine convergence or divergence. So I don't treat the An, Bn as An has to be the smaller and Bn has to be the bigger. I just need to have that understanding component. So the first thing that we're going to do is we're going to identify our An and our Bn terms. Okay, so I always just let An equal the given or the original sequence. And then from there, I'm then going to find a basic series and identify that to be our Bn, so our basic sequence. So because I'm writing An without the summation and Bn without the summation, so those are my sequences, right? So that is how I always will start this particular problem. Okay, so then this right here, so I'm going to take that rule. So that's my AN, and I'm going to let that equal the given, which is 3n squared plus 2. So that would be step 1. So now step 2, I want to find a basic sequence. So I want to find a basic sequence. So how I find a basic sequence is I just get rid of what I call the fluff. And so for this particular problem, what I would consider the fluff is the 3 and the 2, right? And so I can leave the 3, but the plus 2 is the distracting part. So I'm going to go ahead and leave that 3, and I'm going to get rid of that plus 2. And the reason I'm doing that is because our p-series and our geometric are very specific, and that this right here is something like 1 over n squared, right? And if there happens to be a 3 here, no big deal, because that's the same thing as 1/3 and then 1 over n squared. What is not a p-series if I add 2? If I add 2, it is no longer a p-series. So that is what we're doing. Okay. So then once I do that, then I want to determine the inequality of the terms of the sequence. So then now I want to determine the inequality, meaning, is AN less than or equal, or is, hold on. Let me keep it in the same order. Or is AN greater than or equal? Like I want to figure out like which has the larger terms, right? So term by term. So I want to determine the inequality. So I want to figure out like, well, okay, which way should this inequality go? So which one of these generates larger term sequences? Like when n is 1, which one would be bigger? When n is 2, which one would be bigger? So when I look at this, I see that I'm adding 2 to the denominator here, right? So I can see that AN has a larger denominator because I'm adding 2. So if it's a larger denominator, that makes it a smaller fraction. And I don't care about the equality component because like maybe at n equals like 0, it would be equal or, something like that. So I'm always going to put that equals piece because that is allowed, right? That is allowed. So again, that is because I have a larger denominator, so a smaller fraction. So that means AN will generate smaller terms when they have that same domain, okay? So then once I do that, I use reason to determine, like, will that follow the direct comparison test, okay? So now this is when I'm going to be apply the direct comparison test, and I'm going to abbreviate that DCT. So what does that mean? Okay, so now I have to, so this is me thinking, okay, because I don't want to memorize because that gets me into trouble. I don't know about you, but that gets me into trouble. So I know that this series over here, right? So I'm going to rewrite that as an infinite series as part of my justification. So as part of my justification, I'm going to say that I know 1 over 3n squared converges because the power is equal to 2, which is greater than 1, right? So this is back using the p-series information. So I know that the sum of the series 1 over 3n squared, right, that infinite series will converge because the power is equal to 2 greater than 1. So then I already know, so then now in my brain, like what I'm thinking is I know that this one converges by the p-series. That's my basic series. And I know that it is always larger than A, right? So it's always going to be larger than, greater than, or equal to AN. So that means that if these numbers over here are always larger, right? So these numbers are always larger and it adds up to a finite value, then that makes sense that the smaller termed sequence infinite series would converge as well. Okay, so which is what this is saying right here. So what that is saying right there. So because this is all true, then I can make that conclusion that my infinite series of AN converges as well. And that's by the direct comparison test. Okay. All right, so let's take a look at the limit comparison test. So what does that one say? So this is just an alternate. So the direct comparison is very persnickety, right? Like it has to be less than this and greater than that in order for it to converge or to diverge, right? A lot of rules attached to that one. So the limit comparison test doesn't have as many rules, but it definitely has a few rules. Okay, so let's take a look at the limit comparison test. So this one is just saying that you have your two series as long as they're greater than 0. Then if their ratios to infinity is equal to a finite and positive value, then the two series act the same. So that means they either both converge or they both diverge. So they're looking at the ratio, right? The ratio between the two series. And if you get a finite and a positive value, then the series are going to act the same. So if your basic series converges or diverges, so I'm going to always use B for my basic, meaning your good old-fashioned geometric, good old-fashioned P series. So, and then now your modified one, the one that we add 5 to or divide by 4 or whatever, if they have a ratio that is finite and positive, so a 1-to-1 ratio, a 2-to-1 ratio, then the series will act the same. Okay, they will either both converge or both diverge. All right, so let's go through our steps. So our steps start out the same. Okay, so the first thing is we are going to identify what our AN is. So I'm going to always let AN be the original. And then I'm going to find a basic series to let Bn be that basic series. Oops. Find a basic series for Bn. So for this particular problem, so AN is going to equal my original, so 5n minus 3 all over n squared minus 2n plus 5. So now for my basic series, I'm going to get rid of like all of that extra stuff. So what do I call extra stuff? So I'm going to keep the 5n because that kind of controls the numerator, and I'm going to get rid of the minus 3. And then I'm going to keep the n squared, but get rid of the negative 2n plus 5, because I'm going to keep the pieces that are controlling the numerator, keep the pieces that are going to control the denominator. So then my basic series is going to end up being 5n over n squared, which is 5 over n. And so now I want to, determine that convergence or divergence of Bn. Okay, so now that you have a basic series, you want to determine the convergence and divergence of the infinite series of Bn, which I probably should have had that up in the step below or above. All right, so I'm going to make that conclusion over here. So Bn is a P series, right? And so because it is a P series, I know that I'm gonna run out of room. Oh, I'll make it work. All right, so I know that Bn has a power, that's supposed to be an arrow, of 1, right? And so that is equal to 1. So then I know that 5 over n will diverge. Right, so P series, it has to be strictly greater than 1, and it's equal to 1, right? That's the power of 1, so then it would diverge. So then once I do that, then I'm going to go ahead and set up the ratio. So now what I'm thinking about, if I get a finite and positive value, that means that AN will diverge, right? Because they act the same. They act the same. So then we're going to set up the limit of the ratio and evaluate. So here I have AN over BN. It really doesn't matter like which way. Like if you forget, oh, which one should be on top, which one should be on the bottom. Like it really doesn't matter, because whatever finite and positive value you get, you'll still get one regardless of which way you did, right? So if you, for example, write it as AN over BN and you got that answer to be 5, and your neighbor flipped it and they did BN over AN, they would get 1/5, right? They would just get the reciprocal, both of which are finite and positive. So don't feel like you need to memorize like, oh, which one should go on top, which one should go on the bottom. It really will still generate the same conclusion. So we're going to take the limit of an, so 5n minus 3, and then divide that by n squared minus 2n plus 5, and then divide that, right, by 5 over n. And then now I need to figure out what this is, right? And if I get a finite and positive value, then I know that an has to diverge, right? Because it has to act the same. So because bn diverged, right, bn diverged, I'm hoping to get a finite and positive value, which will also tell me an diverges. So that instead of dividing by that fraction, I'm going to multiply by the reciprocal. And then go ahead and distribute. And distribute the 5. And so I look at our common power, right? So it has that common degree in the numerator and the denominator. So then it will just be the coefficients when I take that limit. So for this here, then it would be 5 divided by 5, which is a finite and positive value. So that means that if bn diverged, which it did, then an would have to diverge as well. So the infinite series for an has to diverge. Okay, so let's do 2 more examples here. And so this one just says use the comparison test. So you can do like whichever one you want to do, like limit, you could do direct, it doesn't matter. So I'm going to go ahead and just do direct on this one and then hope it works, right? Okay, so first thing I'm going to do is I'm going to write out my original. So that would be 4n over and then 3n minus 1. And then for my basic, I'm going to get rid of the extra. So in this case, the negative 1 is the extra. So I would have 4n over 3n, right, which is the same as 4/3 to the power of n. So then now I want to decide, okay, well, what's that basic series doing? You know, is it, geometric? Like what would happen here? So if I look at this, so I would look at, 4/3 to the power of n, and I would see it's geometric, and the ratio is 4/3, which is greater than 1. And so then therefore, bn would have to diverge, right? Bn would diverge. And that's because my ratio is 4/3 greater than 1. So I'm multiplying and creating larger numbers that I want to add up to a finite number, which is not going to happen. So then now once I do that, I want to determine that inequality. So I have 4 to the power of n over 3n minus 1, and I want to compare that to the 4 to the n over 3 to the n. So I'm using this version of it so I can like look at them side by side. So because my denominator over here is subtracting 1, so that means this denominator is smaller. So if the denominator is smaller, that means the fraction is larger. So that's the way the inequality would go. And then I know from over here that this generates a sum that would diverge, and it's smaller than this one over here. So if the smaller termed sequence will add up to infinity, then the larger termed one has to as well. So then it falls into that direct comparison test. And so then I can say that therefore my infinite series of an diverges as well. So what I have to always show is what am I using for, like, what's the sequence going to be here? And what's its infinite series going to do? It's going to diverge. I have to show my inequality and then make my conclusion. All right, so let's try to do this one over here. So we'll do B. So for this one right here, so if I say, all right, let's let an equal n over n squared plus 1. And then let's do the same thing for bn. So for bn, what is my fluff? So the extra piece is that plus 1. So that would be n over n squared, which would just be 1 over n. And so what do I know about that? 1 over n. So that would be harmonic. It's a harmonic p series. So my power is equal to 1. And so then I know that it will diverge. Okay, so now I'm going to try direct comparison test again. Okay, so I'm going to look at n over n squared plus 1. And then I'm going to compare that to n over n squared, right? So I'm using this form again so I can determine that inequality pretty easily. So I have a larger denominator because I'm adding 1. So larger denominator adding 1. So that means I have a smaller fraction, right? Larger denominator, smaller fraction. And I know this side diverged. So this is the bigger term sequence and it diverges. And then this is the smaller one. So if the larger termed one diverges, we know nothing about the smaller. It could diverge, it could converge. So that means the direct comparison test doesn't tell me anything. So then I have to do the limit comparison test, but I can still use all the information I already have found, right? So because the direct comparison test was like, didn't work, and now I'm going to try the limit comparison. So I have n over n squared plus 1, and then I'm going to divide that by n over n squared, or 1 over n. And then let's go ahead and multiply by the reciprocal, and feel free to just do that right off the bat because we're always going to be working with fractions pretty much. So if you want to like skip like this step and then just multiply always by the reciprocal, you should do that. All right, and then let me go ahead and finish this out. So that would be n squared over n squared plus 1. They're of equal degree. So then when I take that limit to infinity, I would look at their coefficients, so 1 over 1. So I got a finite positive value, so they act the same. So because bn diverged and there's a 1-to-1 ratio with an, I can then say that an diverges as well. And that would be the justification.